Welcome to this lesson on stopping distances, lesson 16 in forces and space. This is always a topic I've found quite tricky to teach. It always feels like you end up just telling kids stuff and they're not really having to think. But actually, if we continue with the principle that I've been espousing all the way through these videos and this scheme of work, if we think about it in terms of visualizing a certain scenario in terms of our core concepts, Newton's first and second law, hopefully we can give them a really clear picture of what's going on, and hopefully that'll help them remember it better. And again, this is kind of GCSE topic, but I think conceptually it's perfectly fine to go in at Key Stage 3, and it's a nice way of reinforcing some of those core ideas. So what I'm going to do if I'm explaining this to students is I'm going to ask them to imagine a car. So I've got my car traveling along the road and the driver sees a hazard. So we can imagine, I'm going to draw it kind of over here. I want to leave a little bit of space at the side of my page. So maybe a child runs out into the road or something like that. Now, in the first example, we're going to imagine this car is traveling at 30 miles per hour. So I'm going to put V equals 30 miles per hour. And we're going to assume it's traveling at a constant speed. So ignoring the vertical forces, I'm only really interested in the horizontal forces. I'm going to put two forces here like this. So this is going to be the thrust force, let's say, and this is going to be the drag force. And again, it's a nice chance to just reinforce the point that if it's traveling at a constant speed, then the magnitude of these two forces should be equal. Now, what we need to explain to students is that there's a little bit of time between the driver seeing the hazard and the driver managing to take their foot off the accelerator pedal and put it onto the brake pedal and hit the brakes. So after a short amount of time, which I'm going to label like this, we'll have the following scenario. So let's draw our car again. If you don't want to draw a car, if you want to draw it as a little box, that's absolutely fine. Now at this point, after let's say 1 second, which we're going to call the driver's reaction time, and what we want to do here is really make sure we are clear about the difference between reaction time and thinking distance, but we'll come back to that in a sec. Well, our car is still traveling at 30 miles per hour. And what's going to happen here, though, is that the forces are going to change. So the driver's going to take their foot off the accelerator pedal, and so that thrust force is going to go. We're not going to be putting any force forwards anymore. What's going to happen is you're going to have still a bit of drag, although that's not what we're really interested in at the moment, but I'll draw it anyway. So we've still got a bit of a drag force, like this, but we've also got this big braking force. Now, I'm just going to call it friction. I'll put FR for friction. You might want to do a bit of a big diagram so you can write that out, or you can call it the braking force, that's fine. But what we want students to recognise here is that whereas here we had no resultant force, so it carried on at a constant speed, to here, at this point we've now got quite a large resultant force in the negative direction. And I should have said, of course, we're going to take this way as positive for the sake of our if we were to do any calculations. But what we have here is quite a large resultant force in the negative direction. And therefore, if I've got a large resultant force in that direction, well, I'm going to have a large acceleration in that direction. But if an object is travelling and you get a negative acceleration, what that means is it slows down. So this velocity is going to start decreasing. But if I'm going at 30 miles an hour, the problem that I might have is that I might not brake in time to save this poor child. So by the time that I actually stop, which is, let's say, over here, car's changed shape, but anyway, by the time I get to a velocity of 0, well, sadly, it was too late for the child, and I've managed to knock them over. So what we need to emphasize to students is a couple of points here. So firstly, this distance here, you want to label that as the thinking distance. And then this diagram hopefully makes it really, really clear what we mean by thinking distance. It's just the distance it travels while the driver is reacting. We said that was the driver's reaction time here. This distance over here is the braking distance. And that's the distance the car travels while the driver is applying the brakes. And actually, you know, that depending on the size of the force, the braking distance might be shorter than the thinking distance, whatever. The point is, those two together constitutes the stopping distance, and what we really care about on the roads is whether the stopping distance is short enough to save the child. So let's consider a second example. Let's consider another example here like this. This time, the driver is not travelling at 30 miles an hour, they're travelling at 20 miles per hour. So we can label the forces again. The forces are going to be balanced here, so I've got the thrust and the drag. You could point out to students that the drag would be a bit smaller if the velocity is only 20 miles per hour, but we don't need to go into that in loads of detail. So let's imagine we've got the same reaction time. The point that we want to make is, in that time, because the car is travelling more slowly, in this same reaction time, the distance it travels is actually going to be smaller. So we can show that here on our diagram, and hopefully students will see the contrast with the diagram above. For some reason the car seems to have got smaller as well. But by the time it gets to here, remember it's still travelling at 20 miles per hour because the forces were balanced. Nothing really happened during this time, the driver was just reacting. At this point the forces change because the driver hits the brakes. So you've got the drag force, but also this much larger frictional force, which I struggled to draw there, but hopefully you get the idea. That's the frictional force. So you've got this large resultant force, just the same as it was before, but in this case, because you were going more slowly, sorry, that's the resultant force. Let's get rid of that bit. So then you've got this large acceleration. The resultant force is going to be basically the same because the brakes are just the same in these two examples. But because it was travelling more slowly, the braking distance is also going to be a bit shorter. So if this is the child over here, well, it's going to stop sooner because it's not travelling as far, so it doesn't have as much speed to lose, and you've got the same resultant force. So maybe the car stops over here, and by the time it stopped, that overall stopping distance is less than the distance between where the car started and where the child was, and therefore the child is saved. So hooray, we can put, maybe we could draw some sweat falling from the child's face in relief at not being hit by the car. So again, what we want to illustrate to students here is, that may not be the neatest, but what we want to illustrate to students is that this thinking distance when the speed is lower, the thinking distance is shorter. So this distance here is shorter than this distance here. I'll do arrows again. And we also want to illustrate to students that the braking distance is shorter when the speed is lower, because there wasn't as much speed to lose and you had the same resultant force in the opposite direction. So this is the braking distance. I'll just put BD for now, which is also shorter. So we can look at a couple more examples here, and if you just model it in the same way, we can then show why some factors affect the thinking distance and why some factors affect on the braking distance. So let's imagine a third case. We're going to, in fact, I'll leave this one up, and we can, because then we can contrast it. So let's imagine a third case. So we've got the car here like this. We've got the hazard over here like this, so the child. So let's imagine this car is also going at 20 miles per hour, so we're just going to change one thing at a time. If any of you have come across Christian Moore Anderson's book about variation theory, I think this is what he's talking about. This idea that when we want to show students the concept, we just change one thing at a time. We shouldn't change lots of things, just change one thing so they can see the difference. So in this case, it's exactly the same. We've got the thrust forwards. we've got the drag in the reverse direction. Those forces are balanced, as we said before, so it travels at a constant speed. But this time, we might say the driver's been drinking, or they're talking on the mobile phone, or they've got distractions, or maybe they're just a bit old and their reactions aren't quite as quick as they were. So in this case, the difference would be that actually, even though they're traveling at the same speed as here, instead of it just taking 1 second for them to react, the difference here would be that it takes 2 seconds for them to react, which means in that time, 2 seconds in which it took them to react and hit the brakes, they travelled twice as far. So in this case, our thinking distance would be twice as large. But then you can show them, and we'll see whether my diagrams are up to this now. What you can show them then is that when that person hits the brakes, whether they're drunk, whether they're really old, whether they're distracted, whatever, assuming the car is exactly the same, when they do actually hit the brakes, they're going to hit the brakes with the same force as the car in the second example. So this force is going to be just as big as it was. We're going to have just as big a resultant force, like this, and therefore just as big a deceleration. My diagrams are not to scale, but this is what you can emphasize to students. And therefore, I mean, we don't need to do it exactly to scale, but that's about 7 centimeters. So that's about 7 centimeters, let's say. You can show students that the braking distance will be the same. But look, it wasn't quite enough to save the child, even though the braking distance was the same, because the thinking distance was twice as large. The car got to, what, here? And the child was no more. So that's a problem. Hopefully students think that's a problem. So that's b equals 0, and I should have emphasised at this point, when they start hitting the brakes, v is still 20 miles per hour. So that's one case where if the driver was drunk, the reaction time is greater, and therefore the thinking distance was greater, or all those other factors that we've talked about. And then we're going to compare this case again, which is the kind of ideal case, I suppose, to another scenario where instead of the driver being drunk, the driver's perfectly sober, they're not on their phone, they've got perfectly good reactions and so on. But in this case, we're going to imagine that they're on an icy road. So I'm going to come down, I might just zoom out a bit like this because we still want to compare to this example here. So I'm now going to draw my diagram like this. So here's the car. Here is the child. And in this case, their reaction time, let's just add a few of our notes. So we've got v equals 20 miles per hour. Really make this explicit to students. We can show the forces again. It's always a good chance to remind them. It's travelling at constant speed, and we must have these balanced forces. So that's the drag and that's the thrust. In this case, the reaction time again was 1 second. So the car travelled just the same distance as it did in that second example. So let's put 1 second. Let's try and draw the car in a similar place so we keep it consistent. So we had quite a short thinking distance, and I can label that here like this. Thinking distance was quite short again. TD for thinking distance. But if we've got an icy road, or if our tyres are worn, or if there's kind of gravel on the road, something like that, or maybe the brakes are in bad condition, well, the difference here is, and I've forgotten to label my force here, so that's drag and that's friction. Well, the difference here is that if we think about the backwards force acting, so this is going to be the drag again. Maybe the drag just overcomplicates things. But what we really want to emphasize to students is that friction is going to be a lot smaller. My diagram's getting a little bit tiny here, so that's one to bear in mind if you do that in the classroom. But my friction is going to be a lot smaller. So what you want to emphasize, the difference here, is in both of these cases, we said the resultant force was approximately the same. In this case, and you can kind of exaggerate this, the resultant force is going to be less, and therefore the deceleration is going to be less. And again, we're going back to this one, although we said the braking distance was the same here. What that means is if your deceleration is going to be less, from 20 miles an hour to 0 miles per hour, well, that means you're going to travel a lot further. So because that friction is less because of the icy road or whatever else we said, if I just move my thing down, by the time we get to v equals 0 and the car is stopped, it's stationary, well, unfortunately, that braking distance was so long, in this case, because the frictional force was less, that alas, the child again is no more. So this is what we want to show to students, is firstly, the reason those factors like alcohol, phones, distractions, whatever, the reason those increase the stopping distance is because they increase reaction time here to here, therefore that increases the thinking distance and therefore that increases the stopping distance. The reason icy roads or dodgy tyres or brakes or gravelly roads, whatever it might be, increases stopping distance is because there's a lower frictional force, and we can really clearly represent that, and therefore there's a larger braking distance, and therefore the stopping distance increases. And what we can emphasize through these diagrams is the difference between here and here, and this is the kind of guiding question that runs through that whole lesson. Why do local councils reduce the speed limit from 30 to 20? Well, it's because that reduces both the thinking distance and the braking distance, and therefore it makes it much more likely that we won't have accidents that endanger the life of pedestrians and anyone else. So it's quite a lot there. That's one of the longer videos I've ever made for a lesson, but I hope you can see how you can explain that topic really, really clearly in a way that doesn't just get students repeating things back to you without really thinking about what's going on. I hope that was useful. Next lesson, we're going to get on to some exciting stuff. Well, there's a lesson on reaction times, and then we'll get on to projectiles.